So now you know about convolution and how convolution works in the time domain. And just by way of very quick review, the way that convolution in the time domain works is by starting with your time series data, the EEG data, and a wavelet kernel for which we are using a Morley wavelet. And then at each step of convolution, you compute the dot product between the wavelet and the temporally aligned EEG data. So that's the element-wise multiplication and then sum. And the result of convolution goes at the time point corresponding to the center of the wavelet. So here at the center of the wavelet. And then you slide, so this is the one step of convolution, then you slide the kernel over the data by one time point and compute the dot product again, and so on until you get a time series of dot products. And this time series of dot products is the result of convolution. Okay, and then we also discussed that the way that convolution starts and stops is such that the rightmost point of the wavelet is aligned with the leftmost point of the data. So that's the start of convolution. And because the result of convolution at each step is plotted according to the center of the wavelet, the result of convolution is going to be 1/2 of the length of the wavelet too long in the beginning. And then convolution proceeds and slides along like this. At each step, we compute the dot product. And convolution ends when the leftmost point of the kernel is aligned with the rightmost point of the data. And again, because the result of convolution goes in the location of the center of the wavelet, then we end up with a result of convolution that is 1/2 of the length of the wavelet too long. So here we have the result of convolution. And what is typically done, this is not technically necessary in convolution, but it's very useful to cut off the beginning of the result of convolution and the end of the result of convolution. So you end up with a signal that's the same length as the data. So, and of course this is very important, the result of convolution has the length of the wavelet plus the length of the data minus 1. So m plus n minus 1. That's very important. We will see in this video that this is important to remember for doing convolution in the frequency domain. Here I'll skip this, but this was just to illustrate how why the result of convolution is n plus m minus 1. So here we started with the data of length 4, the kernel of length 3, and we ended up with a result of convolution that is 6 points long, so n plus m minus 1. Okay, now with that brief review over, what we are going to discuss in this lecture is convolution via frequency domain multiplication. The terminology unfortunately gets a little bit confusing here, because if you say convolution in the frequency domain, technically that means something else. That actually means computing sliding dot products of Fourier spectra, which is not at all what we are going to do. We are going to do time domain convolution, but it turns out that we can implement it via multiplication in the frequency domain, and that is a lot faster. So it gets a little bit confusing. If I by chance make a mistake and say frequency domain convolution, you will have to forgive me. What I really mean is time domain convolution implemented as multiplication in the frequency domain. Okay, so why are we even going to do this? Let's, before we get into the details, let's discuss why we should do something like this. We learned in a previous lecture that the Fourier transform and the inverse Fourier transform allow us to go from the time domain to the frequency domain without losing any information, and from the frequency domain back to the time domain, again without losing any information. So we can make this whole circle complete without losing or gaining any information. It's just the same information being represented in different ways. Now, so I mentioned in the past that this is very useful because it happens very often that computations can be done much faster and much more elegantly in the frequency domain compared to the time domain. And now we are going to learn one of these situations. So we are going to learn that performing convolution in the time domain is fine, but it's actually faster and better to do it in the frequency domain and then go back to the time domain. This is thanks to something called the convolution theorem. The convolution theorem tells us that convolution in the time domain is equivalent to multiplication in the frequency domain. Actually, the convolution theorem also tells us that the reverse is true, but this is not really relevant for our purposes here. Okay, so here's what we're going to do. We start with a signal. This is our EEG data, and we start with our kernel. And to be clear, these are both time domain signals. Maybe a little bit confused after the previous video because you saw that a Morley wavelet in the frequency domain is a Gaussian, but this is actually just a time domain Gaussian. So these are two time domain signals. This top part illustrates everything that we've done so far. We've done time domain convolution. We took the kernel, we kind of smeared it across the signal, and at each time step during this smearing process, we computed the dot product between the kernel and the signal, and that gives us the result of convolution, which is a time series of dot products. Now, we can take the Fourier transform of this result of convolution, and we would get something that looks like this. So this is just the frequency spectrum of this signal. Okay, so this is nothing new. This is stuff that we've done. Now here is what's new. Instead of doing all this stuff in the time domain, we can go straight to the frequency domain. We can take the Fourier transform of the signal, and we can take the Fourier transform of the kernel. So here you see, now we're treating these independently. We're not doing anything together with these two signals. We take the frequency representation of the signal, the frequency representation of the kernel, and now we pointwise multiply these together. We're not going to sum. This is not a dot product. We just pointwise multiply these two frequency spectra together, and we get something that looks like this. Now, the convolution theorem tells us that this Fourier transform, or this frequency spectrum, is exactly identical to this frequency spectrum. Not that they're sort of close, or one is an estimate of the other. These are exactly numerically the same thing, these two. Furthermore, or this also means we can take the inverse Fourier transform of this frequency spectrum, which is just the multiplication of these two, to go back to the time domain, and this will give us a time domain signal that is exactly numerically identical to this time domain signal, and this was the result of computing the convolution between the signal and the kernel. So the convolution theorem tells us that the multiplied frequency spectra of the individual time series is equivalent to the frequency spectrum of the time domain convolution between these two series, and also this for the inverse Fourier transform. Okay, now maybe you're looking at this plot and saying, this is ridiculous. Why would I do all of these steps when I can just do convolution? Because typically we don't really care about this. We just want this. So why should I do 1, 2, 3 steps when I can just do one step? If we didn't have the fast Fourier transform and we were just using the normal discrete time Fourier transform implemented manually, then yes, you would be crazy to do all of these extra steps when you can just do convolution. But the fast Fourier transform is so fast and so efficient that these 3 steps together are orders of magnitude faster than this. So from now on, we will basically never be performing time domain convolution. And you, in your actual data analyses, should never perform time domain convolution. You should always perform frequency domain convolution. It's much faster and it gives you exactly the same result. So let's see a few examples. So the interesting thing about this is that last time or a few lectures ago, we learned about how to think about convolution in the time domain as taking this kernel and kind of smearing it across the signal. And the result is something that has the characteristics of the signal and also has the characteristics of the kernel. Now, when we think about convolution as implemented in the frequency domain, this gives us a whole different way of thinking about what convolution actually means and what it does and how to utilize it. So now let's discuss this. So here we have a sine wave and here we have a Gaussian. And now when we perform convolution between the sine wave and the Gaussian, we get a signal that looks like this. This is a dampened signal. It has exactly the same frequency, but the amplitude is smaller. Here on the right side, we have exactly the same signal as here, so this signal is exactly the same. Here we have a very similar kernel. It's still a Gaussian in the time domain. So you don't have to worry about the amplitude scaling. That isn't really important. But it isn't relevant that, that this Gaussian is wider than this Gaussian. And now when we perform convolution, the result is just a flat line. So we no longer have a sine wave, we just have a flat line. Now you can see it goes up here and it goes down here and same here and here. These are actually edge artifacts. We haven't really discussed edge artifacts in detail yet, but we will in a future lecture. These are edge artifacts that always happen at the boundaries of your time series when you're doing convolution or Fourier transform or many other analysis methods. So you don't have to worry about those. You can ignore these edge artifacts. Now the interpretable part is the flat line here. So here's the question. Why is the convolution with the narrow Gaussian and the sine wave, why does that produce a sine wave with the same frequency but a smaller amplitude, whereas with the wider Gaussian, the result of convolution is a flat line? If you're thinking about convolution in the time domain, it's a little bit difficult to understand why this is happening. You can sort of think about it as, like the integration time is wider here, so you end up with more positive values and negative values in the same multiplication, and that's why it comes to 0. I think when we think about, or when we implement convolution in the frequency domain, this will make much more sense why you get these different results. Okay, so what you see here is the frequency representation of the kernel. That's the Gaussian. So Gaussians in the time domain have this kind of negative exponential shape in the frequency domain. And here's the time domain representation of the signal. This makes sense. We just have a sine wave at 20 hertz, and so it's just a big bar at 20. It's difficult to see from this plot, but if you look at this zoomed in plot, you can see that these two spectra overlap a little bit. There's not a huge overlap. But when we pointwise multiply all of these elements together, so here we're multiplying the frequency characteristics of the Gaussian by the frequency characteristics of the sine wave at here, and so of course the sine wave is 0 or very close to 0 everywhere except for 20 hertz, but there is a little bit of overlap here. And now we do this pointwise multiplication. This is the result of the multiplied spectra. You can see the y-axis scaling is much smaller than here. So this is a very small overlap, but it is non-zero overlap. And now when we take the inverse Fourier transform of this spectrum, we get a sine wave that has the same frequency as the original signal, but a dampened amplitude, a smaller amplitude. So now when we go to this case, we see that the wider Gaussian in the time domain has a sharper or steeper roll-off in the frequency domain. So this Gaussian is now already at, or the frequency representation of this Gaussian has 0 Fourier coefficients close to 0 already by like 8 or 9 hertz or so. By the time we get up to 20 hertz, you can see there's really no overlap here, unlike in this case. So there's really no overlap. So when we do the pointwise multiplications, we get basically nothing. So you could actually zoom in further and you would see that there are very, very small non-zero elements here. That's what's producing this, these edge artifacts. But the important point to notice is that there's no overlap here at 20 hertz, and so we just get a flat line here. There's nothing. Let's look at another example, but now with real EEG data instead of with a pure sine wave. So it's very similar to the previous example. We have our real EEG data here. We have a Gaussian in the time domain. And here we see the individual Fourier spectra, the frequency spectra of the Gaussian and the EEG data in black. And now when we pointwise multiply these together, you can see here what's happening. The lower frequencies are relatively preserved. As we go to higher and higher frequencies, they're more and more attenuated because the Gaussian is going down. And by the time we get to 18 or 17 hertz or something, the frequency representation of the Gaussian is basically 0. And so the pointwise multiplication of these is basically 0. So we're just eliminating all of these higher frequency components of the signal. And that is why the result of convolution gives us this low pass filtered version of the signal. All right, one more example, and then we're going to switch to MATLAB. So in this example, we're going to use a Morley wavelet. And if you remember from the previous video, a Morley wavelet is a sine wave that's multiplied by a Gaussian. And the frequency representation of a Morley wavelet is a Gaussian. So this is the frequency representation of this Morley wavelet. Now, again, the same EEG data. And here we have a Gaussian in the frequency domain. So this is our representation of the Morley wavelet. Here is the spectrum of the data. Now we pointwise multiply them together. So now this is very similar to the previous examples, except we are not just high pass filtering, we are in fact band pass filtering. The higher frequencies get attenuated, but also the lower frequencies get attenuated. And now you see the result of convolution between this wavelet, it looks like it's maybe at 7 hertz or something, is the bandpass version of this signal. And you can see that it looks like what you would expect for a bandpassed signal. And this is the reason why wavelet convolution is effectively bandpass filtering. So I hope this now gives you a different way of thinking about convolution and wavelet convolution in the context of time frequency analyses. So the 3 steps of wavelet convolution via frequency domain multiplication is to take the Fourier transform of your 2 signals, multiply the Fourier spectra together point by point, so frequency by frequency, and then take the inverse Fourier transform to get back to the time domain. And of course, you will never ever forget that the length of the result of convolution is n plus m minus 1. It's the length of the data plus the length of the wavelet minus 1. And this is always true whether you are doing convolution in the time domain or whether you're doing convolution via frequency domain multiplication. All right, so let's switch over to MATLAB and take a look at this. So here we load in our EEG data, and we specify a channel and a trial. These are just randomly picked values. Here I'm just grabbing the data from this channel and from all time points and from this trial. This is really just a convenience thing, so we don't have to keep writing all of this code everywhere else in the script. Okay, so we can run that. Now what we're going to do is create our Morley wavelet. And remember, we have to create a complex Morley wavelet, so we haven't yet discussed how to extract power and phase information from complex Morley wavelets. It's very similar to how we do it for complex Fourier coefficients. So, of course, if you try to run this line, it's going to give you an error. So we are missing lines 20 and 24. So if you're up for a small challenge, I encourage you to pause the video here and try to complete these lines to make a Morley wavelet. And before you finish, to make sure that you got it right, you should plot the real component of the wavelet so you have visual confirmation so you know what it looks like. All right, so let's see. So to create a sine wave, we know it's going to be something like 2 pi f, and here I'm getting f from this variable here, times time. So we know it's going to look something like that. Oh, and time is up here. I just created this to go from minus 2 seconds to plus 2 seconds in steps defined by the sampling rate of the EEG data. So I know it's going to be something of this form, but because we need a complex sine wave, then I know I'm going to have to add Euler's formula, so we do e to the I times this thing. So that gives us our complex sine wave. Now we need to create our Gaussian. So we know it's going to be e to the minus t squared over 2s squared. So let's see, we need e to the minus time squared. And I'll put this in parentheses so we don't get confused. Over 2 times s, and we just created s on this previous line, 2 times s squared. And I'll also put this in parentheses. It's very useful to use parentheses here because, for example, if you would do something like this, then the way that MATLAB is actually interpreting that is like this. So it's dividing time squared by 2 and then multiplying by s squared, which is not what we want. We want to keep the 2 and the s together like this. All right, so we run that line. We don't get any MATLAB errors, so that's good. And now for a sanity check, we want to plot time and the real component of the complex Morley wavelet. And that looks very good. That's exactly what we expect it to look like. Okay, here in this cell, it starts on line 29, we're going to define the convolution parameters. So here we get the length of the data, the length of the kernel, which is the wavelet, and the length of convolution, which you now know ad nauseum is length of the data plus length of the kernel minus 1. So now here we get to the meat of convolution via the frequency domain, and you can see already that there's a lot less code than we would have needed for, or that we needed for time domain convolution. All we need to do is take the Fourier transform of the Morley wavelet, complex Morley wavelet, and now we have this line where we divide or we amplitude scale the Morley wavelet by its peak. This just scales the frequency spectrum of the Morley wavelet to have a maximum of 1. This step is not necessary, but it is useful because it will ensure that the result of convolution is in the same units as the original data. So that means that if the data are in microvolts, the result of convolution after amplitude scaling like this will also be in microvolts. You can try it again if you want without doing this amplitude scaling. You get exactly the same result. It's still a valid result, but the units are not in microvolts. They're scaled. Okay, and here we take the Fourier transform of the data. Now what you can see in the Fourier transform of the data and the wavelet is that we are not performing the Fourier transform with the n corresponding to the original n. Instead, we are using the second input to the function FFT to tell MATLAB that we want to perform this Fourier transform using the number of points corresponding to n plus m minus 1. Now MATLAB, the fast Fourier transform function, knows that if this is longer than this, which it is, so this is 640 points long, and nconv is 1600 points long, MATLAB will know to zero pad data and zero pad the complex Morley wavelet for you, so you don't have to do the zero padding yourself. All right. Of course, if you try to run this code, you get an error. Now here's where we want to do convolution. So if you'd like to pause it, then go for it. Okay, actually, I had to look down here because I forgot what I'm supposed to fill in here. Okay, so so the meat of convolution is really just taking the pointwise multiplication of the two Fourier spectra. So we have data x times complex Morley wavelet x, and that's it. It's very simple, very straightforward. I was a little confused because typically you would actually take the inverse Fourier transform right here in this same step. So then you get it all done at once. We don't want to do that here just because below I'm going to be plotting the individual Fourier spectrum and the spectrum of conv, so you'll see. Okay, so now we run this cell and it works. And now here we're just going to do some plots. So here's the frequency spectrum. I should have put some axis labels in here, but you'll have to forgive me this time. This is the frequency spectrum of the single trial of EEG data. This is the frequency spectrum of the wavelet. And this is the pointwise multiplied frequency spectra of the two. All right. Now we go back to the time domain. this was just to remind you that the length of the result of convolution is longer than the number of time points in the signal. And so what we want to do is cut the first part of convolution and the last part of convolution off, and to get us back to a result that is the same length of time as the original data. This stuff sometimes gets very confusing to talk about. Okay, and then we plot the result, and you can see this looks like a bandpass filtered version of this signal. Now this is just one trial of data, so it's a little bit noisy. So the result, it also looks a little bit noisy, but there it is. Let's see. Before we finish, we have to discuss two super duper really a lot important things that you can never forget about wavelets when performing wavelet convolution. The first important thing is that the sampling rate that you use to create the wavelet has to be the same sampling rate as the data. And the second important thing is that the wavelet has to be centered it has to be centered. I will show you both those things in a minute. Of course, you will never forget that the length of the result of convolution is n plus m minus 1. So let's play around with these things in MATLAB a bit. So here we loaded in the data, and the data sampling rate is 256 Hertz. And so here in this cell, we create the Morley wavelet with a sampling rate of 256 Hertz. Now let's try to see what happens if we change the sampling rate to 1000. So this is awkward, right? Because the data have a different sampling rate than the wavelet. Now if we plot the result again, we can see this immediately doesn't look right because this is a very low frequency component, but the wavelet we set to be 6.5 Hertz. So in fact, there should be approximately 6.5 waves between 0 and 1000 milliseconds, but we only see like 1.5 or so. And so, yeah, so this is because the sampling rate of the wavelet is about 4 times higher than the sampling rate of the data. So we can try this again. This is a very extreme example, but it will illustrate the point. Now we're specifying that the sampling rate of the wavelet is 20 Hertz. And now you can see that this result is also completely screwed up because here we should have 6.5 cycles between 0 and 1 second, and we have lots and lots of cycles. I will let you plot these wavelets with different sampling rates to see why this is the case. But for now, I just stress that the sampling rate of the wavelet has to be the same as the sampling rate of the data. Okay, so there's the normal result. The next thing we're going to try is uncentering the wavelet. So if you remember, I told you that it's useful to have a convolution kernel with an odd number of sample points. And the way to do that, very simply, the easy way to do that is by defining time to go minus something to plus something, and then you're going to have an extra number of 0 in there. Okay, so now why don't we plot the wavelets? We can say plot time real wavelets. Oop. Oh yeah, it's not called wavelet, it's called C complex Morley wavelet. So you can see that the wavelet is centered at 0, but even if you would plot this without the time vector on the bottom, you can still see that the wavelet is centered at 0. So there's the same amount of time here as there is here. So each step of convolution, each step of convolution in the time domain, now you can see it's useful to understand convolution in the time domain and as implemented in the frequency domain. Each step of convolution is going to plot the result at the center of the wavelet, which is going to be right in here. Okay, now what we're going to do is uncenter the wavelet. So I'm going to say that the wavelet time goes from -2 seconds to +3 seconds. And now we can look again. So now let's first plot it like this. So now maybe when you look at this, your intuition is to say, well, the wavelet's still centered at 0 because here is 0, so and here's the center of the wavelet. But actually, remember that in convolution, either in the time domain or in the frequency domain, we do not actually see these values. All we see are these values, or all we have to go with are these values. And so really, the convolution is going to go like this. So now the center of the wavelet, let's see, this wavelet is around 1,300 points long. So the center of the wavelet is somewhere around here. So that means that each step of convolution in the time domain, the result is going to be plotted here. But this is weird, right? This is, you should already feel that this is wrong, because that means the frequency characteristics from previously in time are going to go into the estimate that happens here. So we're going to get a big phase shift, a phase offset between what's really happening in the data and what we see in the results. So we can run this whole script. Actually, why don't we run it first with the correct way, so the wavelet is centered. And now you can see here, so from around 800 to 1,000 milliseconds, there's really no or very, very little 6.5 hertz component. So this is pretty flat right here. So that's going to be our anchor point, our visual anchor point. Now watch what happens to that when we uncenter the wavelet. Now all of a sudden, what was flat here is now flat here. So in fact, we phase shifted this thing by, half a second or so. And this is just because we changed the time characteristics of the wavelet. So I'll let you play around with this on your own and experiment with other values and other sampling rates and their effect on the data. But the important points to remember here are that the wavelet should always have the sampling rate corresponding to the sampling rate of the data, and the time and the wavelet has to be centered within the x-axis. And the easiest way to do this is by defining time to go minus something to plus the same thing. So -2 to +2. Okay, and I think that was it. So I hope you found this lecture educational and enjoyable. We are getting very close to being able to do a full time frequency decomposition of our time series data.